Welcome back, everyone. If going through this chapter has made you feel like you were on a roller coaster, slung around all over the place between volumes and areas and work and all sorts of other crazy ideas, then you'll be pleased to discover that today you're going to feel like you're on a seesaw. So let's get started. Moments in center of mass. So, what in the world is a moment? So, the physics definition of a moment is it's the tendency of a body to rotate around an axis. The physics formula that we're going to use, remember, everything we're doing in this material is using an old formula that works in a situation where things don't change and um, applying it to situations where things do change so we can use an integral to solve the problem. So the formula here is the moment of a point about an axis is the distance to that axis times the mass of the point. Right? Okay, what in the world does that have to do with a seesaw? Well, if you think back to when you were in elementary school and you would go into the playground and you would sit on a seesaw or teeter-totter or whatever we called it, then what would happen is, at least this was my experience when I was a child, I would sit on the end of the seesaw and someone would sit at the other end, and the ideal thing is that you both weigh about the same or at least have the same moment so that it wants to balance. In that case, that's when it's fun because one person will push up and the other person will push down, and it just sort of balances back and forth. As you push, then it doesn't just always end up with one person stuck up in the air. Now, of course, what happened when I would get on the seesaw is I was fatter than the other kids. So I would get on and it would immediately drop to the ground and the other end would shoot up into the air. And the other person I was trying to do the seesaw with would be frustrated because they're dangling up in the air, stuck up because I was too fat. So how do you fix it, right? What happens when you have a fat kid like me on the seesaw? Well, there's two ways to fix it. Either, right, the fat kid has to scoot up a little bit toward the axis, or the other kid was more often what would happen would try to scoot back, right? So imagine that you have a skinny kid, right, and he has a smaller mass. Then he compensates for having a smaller mass, right, by increasing his distance to the axis. Or if you were like me and had a big mass, then you made your distance to the axis shorter, right? And that would let you make your moments more nearly equal, which made it much more fun because then you could seesaw back and forth. Right? So what we're going to be working with is a two-dimensional area or region, just like we did back when we were talking about finding the area between two curves. And we're going to pretend that this little region or area is perfectly flat. So there's a name for something like that. A lot of times in mechanical engineering or something, they'll call something like that a lamina. As same place you get the word lamination, like when you laminate something, means you put like a thin film over it, right, and encase it in there. Like I have a bunch of baseball cards, and they go in the case, and it's like they're laminated. The when you laminate something, is that flat thin part of it. So what we will have is a lamina. That means a flat thin film itself, and it's sitting there like a graph, an area between two curves. And we're going to calculate its moments around each of the axes, and more importantly, its center of mass. So because this is like an area between two curves, we can calculate its moment around the x-axis or around the y-axis, um, and we can calculate its center of mass. Now, we'll always assume that these things have no thickness, right? So they're just a flat, not thick at all lamina, and that the density is 1. Okay, so why should the density be 1? I have no idea why every book does it this way, but they all do. They all assume that the density is 1, in which case then mass is the same as area, because mass should be the density times the area. And so you assume the density is 1, then then you get the mass and the area are the same thing. I don't know why books do it this way, because you don't need to. You could assume that the density was a function that varied with x. It would just go into the equation just like anything else. But for some reason, every calculus book does it this way. So we will too. So how do we find the center of mass? Now, that's an interesting thing, right? This is a much more interesting question than seesaws and balancing back and forth. Well, the center of mass, of course, that's the point where your region would balance. If you could imagine taking your region and holding it up at that exact one point, it would completely balance in all different directions. So why should the equation look like this weird thing? This does look weird, okay? So the center of mass, well, first off, x bar comma y bar is the coordinates for the center of mass. Why the bar? Has anybody thought of the bars before? So you may have run across a variable with a bar over it um, when you talked about statistics or probability or something at one point. So with the little bar over it, this is like the average is what the little bar means. So this is like the average x and the average y. That's why the bar is there. So how do you find x bar, that sort of average x? Well, oh wow, look at this. This says my. What in the world is the y? The moment around the y-axis divided by the mass. That is weird. Why the y, right? And of course, for y bar, it's mx over m. And it looks like it's completely backwards. Until you stop and think about it for a second. What is my, right? That's the moment around the y-axis. So if I took this m, I'm circling there, and moved it over to the other side, then this formula would become my equals x bar times m. Oh, now wait a minute. What is that? That's x bar times the mass. Well, that looks like it fits our original formula, right? Because the moment around an axis should be the distance times the mass. And m is the mass, x bar is the distance. The distance to what? Well, this may seem a little weird, but if you think about what we did when we were talking about volumes and areas, the x coordinate is the distance to the y-axis, right? Imagine drawing a point, and if you have an x coordinate that's 7, that means you've gone to the right 7. You've gone 7 units away from the y-axis. The same way that the y coordinate is the distance to the x-axis. So that's why this weird formula here looks odd, because we've switched, it looks like, on x's and y's, but we really haven't. We're just using the formulas. Okay, this desperately needs an example. I've talked a long time about about laminas and seesaws and stuff. Let's work a problem. So here's a region bounded by 2x and x squared. If you remember the video where we were calculating volumes rotated around various axes, this is the same region that we used in that video. So let's find the moment around each of the various axes. So what we're going to do, of course, is break things up into pieces, because our formula only works for the moment of a point, right, around an axis. And I don't have a point. I've got a whole region. And the distance to the axis changes, right? Right here, the distance to the y-axis. Say I talk about the y-axis first. The distance to the y-axis is the x-coordinate. So it's not very far here. By the time I get over here, it's much bigger. Eventually, the distance is 2, right? According to my graph, by the time I get over there. So what's changing is the distance to the axis, right? And also possibly the mass, right? Because remember, mass is density times area, and we're going to assume the density is always 1. So the mass will be the same in our case as area, even though that doesn't always have to be the case. We'll assume that it is. So here's what I'm going to do. I'm going to break this up into pieces, little rectangles like we did ages ago, it seems like now. And then I'm going to replace that rectangle with a dot. Okay, wait a minute, where did the dot come from? Well, our formula is for the moment of a point, not the moment of a rectangle. So what I'm going to do is I'm going to replace that rectangle with a dot, centered right in the middle of my rectangle. In fact, right at the center of mass of my rectangle, right dab smack in the middle. Okay, so there is my rectangle with its dot. And I'm going to find the moment of that dot around the axis. Then find the moment of all the other rectangles and dots that I could make and add them all up. The cool thing about moments is they add up, just like areas do and just like volumes do. So you knew that from seesaws, because if you put 3 kids on a seesaw, right, the moments just add up. Okay, how do we calculate this moment? Well, I need moment around the y-axis. That would be the distance to the y-axis, in other words, the x-coordinate, times the mass. So distance to the y-axis is just the x-coordinate of my dot. The mass is, well, just the area of that rectangle times the density, which is 1. So I get 2x minus x squared dx. Now, where did that come from? Well, back in the video where we found areas of between curves. So I need the height of this rectangle. So that would be the big number, right here. The difference is the y coordinate. So the big y coordinate there is 2x, the line. The smaller y coordinate is right here. That's the parabola, x squared. So 2x minus x squared, and the thickness is delta x. That gives me my area. Multiply that by 1 to get the mass, and multiply by the distance to the y-axis, which of course will just be x. That gives me the moment of that one red dot. If I add up all those possible red dots that I could draw, then let the rectangles get smaller and smaller and smaller, use more and more of them. I get an integral in the limit, and finally I have an integral which gives me the moment around the y-axis. Okay, so same idea works for the moment around the x-axis, but there's one wrinkle, okay? You may notice that I've drawn a bigger box for the distance there. That's because I have to think a little harder about what the distance to the x-axis is. Of course, the mass is going to be the same because it's the same dot, right? It's the same dot there, and the mass is fine. The problem is, what's the distance between this red dot right here and the x-axis? Well, at first guess, what people often say is, oh, you should, it's halfway between these two, so you should do the line minus the parabola and cut it in half. Well, that would give me half of this distance, right, or this distance that I'm marking on my screen there. But that's not what I need. I need the distance from the dot to the axis, right? Okay, so how do we find this? Here's by far the easiest way to understand this. Remember when I talked about putting the bars over things, that those were averages? Think about what an average is for a second. An average is between two numbers. An average is the point halfway in between, right? So what I need to find this dot's y-coordinate is it's the y-coordinate halfway in between the line and the parabola. In other words, what would happen if I took the y-coordinate for the line, the y-coordinate for the parabola, and averaged them together? Well, that would give me the y-coordinate right in the middle. And that's what I need. The y-coordinate of the dot is the one halfway in between the line and the parabola. So I average these two together to find the y-coordinate of the dot. The y-coordinate of the dot is the distance to the x-axis. So this is why I get 2x plus x squared over 2. And again, this may look weird that I'm adding the two together, but again, what I'm really doing is averaging the y-coordinates. So I find the y-coordinate of the dot right in the middle of the rectangle. Then integrate that from 0 to 2 and we're good to go. If I need to find the mass, okay, well, that's the same as the area. We did that ages ago. Just 2x minus x squared dx, and integrate that from 0 to 2. If I need to find the center of mass, then what I would probably do on an exam is write down my equals this integral, mx equals the other integral, m equals the other integral, and then say that x bar is my over m, and y bar is mx over m, and not recopy the integrals. One reason is because sometimes when people write integral divided by integral, they do incredibly insane stuff like try to cancel the integral signs, which, that just means that you get an F. Right? That can't possibly happen. You don't divide and cancel the integral signs. And I don't want anybody to risk accidentally doing something crazy because they're under stress and they're in a hurry and they're trying to get onto other problems or something. So you just give me the formula. So oftentimes what I'll do on a test question is ask for my, mx, m, and the formula for the coordinates of the center of mass. Makes sense to everybody, right? One of the things that's important to remember on the exam is to label your various integrals. So if I ask you to find the moment around the y-axis, the moment around the x-axis, and the mass, make sure you tell me which of the three integrals is which. Because if you don't tell me which, I'll have to count off some because I don't know that you knew which integral was really which. So make sure that you label your integrals if you have to calculate all three of them. Okay, one more quick example. Here's a region that's not just in the first quadrant. It's bounded by the line y equals x plus 6 and the parabola y equals x squared again. So these cross, right, when x is at -2 and when x is 3. And we could find those intersection points by setting x squared equal to x plus 6 and doing some algebra, but we're not going to bother to do that. We're just going to break this up into rectangles, put a dot right in the middle of the rectangle, and use our formula that the moment of a dot, moment of a point around an axis, is the distance to that axis times the mass. So my should be the distance to the y-axis times the mass. Right? What's the distance to the y-axis going to be? Well, that's always the x-coordinate, so just x. The mass, well, that's the area times 1, so in this case, the line, x plus 6, minus the parabola, x squared, multiplied by the 1 for the density, which we won't even bother to write down, times delta x for the thickness of our rectangle. And there's our mass. And we integrate from -2 up to 3. For mx, we find the distance to the x-axis and multiply that by the mass. And remember, what's the distance to the x-axis of my little dot? There's my little dot. How do I find the distance to the x-axis? That's the y-coordinate of this little dot. What's the y-coordinate of the little dot? Well, it's the average of the ones above and below it. In other words, the y-coordinate of the dot is right smack in the middle between the y-coordinate here, which is x plus 6, and the y-coordinate here, which is x squared. So if I average the x plus 6 and the x squared, I get the y-coordinate right there. And that's the distance to the x-axis. My mass is the same as it was before, and I integrate from -2 to 3. If I want just the mass, I just integrate the mass part from -2 to 3.